It's a pleasure to have Eleny Ionel from Stanford, who will tell us about counting embedded curves in threefolds.
Thank you so much for the invitation. It's a pleasure to give a talk here, and it's very nice to see all friends. So let's see. So the talk for today, so it's going to be a broader talk. I'm going to talk a little bit about some background and motivation for the problem. And this is something that I've talked about before. There are some new developments, and I want to focus mostly on the new developments, but I still want to start with sort of the background and the motivation. So we're going to start with a symplectic manifold, X omega, and we're going to choose an almost complex structure, and we can choose it to be tamed by omega, or if you prefer compatible by omega, it's a more restrictive condition, but it works for tamed with omega. And in fact, every time you have such a pair, you can also choose the corresponding metric, so that will be important. Let's see, there are some sounds in the background. So, so what we want to do, we want to count J-holomorphic curves, pseudo-holomorphic curves in this symplectic manifold X. But really, what does it mean? What exactly does it mean, a curve? Okay, and actually there are several perspectives. Okay, so I have them, several perspectives you can think when you think about the curve. What could a curve be? Going back to Gromov in the 80s, at the beginning of 80s, we want to think of J-holomorphic curves as J-holomorphic maps in. Maybe, oops, I have a picture. I want, sorry, I drew this picture earlier. So we have a map in from a genus G Riemann surface into X. Maybe this is the image, maybe it's singular. So we look at maps in, which are holomorphic, right? So they satisfy this equation, d bar f equals to 0, of course, up to reparameterizations of the domain. Okay. But there is another perspective. If you want a more naive perspective, you can just look at the subset, right? As the image, as a subset. Of X, okay, and somewhere in between, you can also, you don't really look at it as a map mod reparameterization, but you carry a bit more information than just the image. Going back to Taub's, motivated by his work relating Seibu-Witten invariants to the Gromov-Witten invariants, we can also look at the images. We can, by a curve, we can mean the image of a J-holomorphic map, but counted with multiplicities, right? So we're going to actually have some multiplicity here. So if this map is like 3 to 1, then onto its image, then we will also record not just the image, but also the multiplicity, and we regard this as current, right? So we can, if you want, we can regard a curve. By a curve, we can mean either a map mod reparameterization of the domain, we can mean just a subset, or we can mean, sort of the image, but with multiplicity, perhaps regarded as a current, like a delta function supported on this curve. Okay, and so these are different perspectives of what one curve, what one mean by curve, and in fact, they give you, if you want, different answers, if you want, on different notions of different topologies on the space of curves, different notions of convergence, different compactifications, and so on. So let me first remind you, or at least let me first mention, the classical approach due to Gromov, looking at maps, J-holomorphic maps, up to reparameterization of the domain. So this is not a compact space, but one can compactify it by allowing maps with nodal domains. So here is a picture of a map from some genus G. This would be a genus 3 curve, a nodal domain, and a map in, and this is maybe a picture of the image. I mean, I don't know, I kind of try to draw it. And so we have some genus G domain, and the image would represent some homology class A in H2 of X, right? This is our target X. And then we can look at the moduli space of such pseudo-holomorphic maps, well, up to reparameterizations of the domain. And this has a natural topology called Gromov topology. What it means, I mean, I'm not going to define it to you, but there is a notion of convergence where what it means for a sequence of maps with genus G domains to converge to a map, for example, with a nodal domain. Okay? In particular, it means that their images certainly converge, for example, in Hausdorff distance. Okay? Any other questions? I mean, sorry, any questions about this? All right. So then this leads to the notion of Gromov-Witten invariants. And for the purpose of this talk, I'm just going to restrict to Calabi-Yau threefolds. So threefold, well, actually means 3 complex dimensions, which means 6 real dimensions. Okay. And Calabi-Yau for me will just mean that the first term class of this manifold is 0. Okay. And the reason why these are very nice spaces to consider is because if you look at the dimension, the expected dimension of the space of solution, If you look at the expected dimension of the moduli space of genus G curves representing a homology class A, which are J-holomorphic, this is always zero dimensional, independent of the genus and the homology class. So all dimensions sort of this J-holomorphic maps moduli parameterizations, they're all zero dimensional. Okay, so one could count. Okay, so what we would like to count, we like to count the number of such maps for a generic parameter J. Unfortunately, as many of you know, there is a problem with multiple covers. If you look at pseudo-holomorphic curves or J-holomorphic curves, every time you have a J-holomorphic curve, let's say it's C, I can always consider covers of it. So they could be even branch covers. I'm going to try to draw it maybe like that. Maybe this is a threefold cover. Okay, if you consider a branch cover of it, that will also be holomorphic. Okay, and so you expect this come in families. For example, you can move the branch points around. So they cannot possibly be cut transversely. You are expecting a zero-dimensional space of solutions, and every time you have a solution, all its covers are also solutions. So, and they come in families, so it can't be cut transversely. And then on top of this, they also, some of them, many of them have automorphisms. Okay, so covers have like depth transformations, for example. A degree 2 covers have a Z2 automorphisms and so on. And so this sort of, obstructs sort of the naive count of such elements of such J-holomorphic curves. Okay. So what is the solution? One solution is to turn on perturbation. So you perturb the equation, and then you count the number of perturbed solutions. So you get the Gromov-Witten invariants for generic perturbations. You count the number of solutions. You have to count them with sign and with weight, 1 over the automorphism, right? They may still have automorphisms, and in particular, you're going to get a rational number. Okay. Now, maybe a more intrinsic way to do this. I didn't write it on my slide, but a better way to do it that will be convenient to think of during my talk is to define the Gromov-Witten invariant. There is something called the virtual fundamental cycle. This is a homology class. You can show that this space of solutions, this moduli space has what's called the virtual fundamental cycle, which is a homology class. And then you can just integrate this homology class, MAG. It's called virtual fundamental class. You integrate against 1. Okay. And this is it's a rational check homology class. So the answer, if you pair it against the cohomology class 1, you get a rational number. Okay. So that will be another definition of it. Okay. But regardless, this gives us a well-defined invariant, and if that's what we care about, that's fine. But obviously it's going to overcount these multiple covers, right? Because we have this whole family of multiple covers. We turn on perturbations. If you think about defining this turning on perturbations, you turn on perturbations. Some of them will deform and give you solutions to this perturbed equation. So it clearly sort of overcounts these multiple covers. Okay. Any questions so far? So that's sort of a brief reminder of Gromov-Witten invariants, especially for Calabi-Yau threefolds. Okay. So the main motivation for our project was this Gopakuma-Vafa conjecture, and I said many of you have heard me talk about this earlier on. So this is a conjecture motivated by string theory around 98 by Gopakuma and Vafa. And what they conjectured, roughly speaking, is that for any Calabi-Yau symplectic, well, they were working with complex Calabi-Yau threefold, but for any symplectic Calabi-Yau threefold, there should be some other collection of invariants. They call them BPS states. They have some physical interpretation. And there should be also a very specific transformation that takes the collection of Gromov-Witten invariants into this collection of these other invariants called the BPS states. I denoted them by NAG. So that if you make this transformation, so it's an invertible transformation, they carry the same amount of information, but these BPS states carry this information in a much more efficient manner. They satisfy sort of these nicer properties. They satisfy what's called integrality. In other words, they are integers, while the Gromov-Witten invariants are rational numbers because of those automorphisms. These guys are actual integers. Okay? And not only that, but they satisfy a finiteness property. In other words, if you fix the homology class, then they vanish in large genus. So they're only finitely many non-zero in each homology class, right? So this is a more efficient and a nicer way to encode the very same information as Gromov-Witten invariants. Okay? And really, if you look at this formula, it almost looks like perhaps these guys would be counting embedded curves. That's not quite the case. or whatever, simple curves, things which are not multiple curves. That's not quite the case, and I'll get back to it. But if you wanted to know, here is the formula for the specific transformation, just for reference. So if you take the Gromov-Witten invariants and you assemble them in this kind of generating function, then you re-expand the series in terms of this other basis of power series, okay? And you get this coefficients NAG. Their conjecture is that if you do this transformation, so just think of this as a transformation like a Fourier transform or something, right? But anyway, it's a very specific transformation that takes this collection of rational numbers into this other collection, if you want, of rational numbers. And for the purpose of the talk here today, we'll define this NAG as a result of this transformation. I should say there is actually extensive work making sense, defining this BPS states along the lines conjectured by Gromov-Witten, especially in algebraic geometry. It's not, the story is not fully complete. They should count somehow curves with bundles over them. There are many approaches. In algebraic geometry, there are several other kinds of invariants that were introduced: Donaldson-Thomas invariants, Panhari-Pandey-Thomas invariants. They are not exactly equal to this BPS states, to this n, but again, they carry the same amount of information conjecturally as the Gromov-Witten invariants, and there are very specific transformations that relate, one set of invariants to the other set of invariants. So, for the purpose of this talk, we'll just take this NAG to be defined by this transformation. And so we'll take this Gromov-Witten conjecture to mean that if you take the Gromov-Witten invariants and you transform them by this formula, and you get this other collection of invariants, this new collection of invariants satisfy both integrality and finiteness properties. Okay. So this is very similar to what happens. This conjecture is very similar to what happens in 4 dimensions. So Taubes has proved around 96 or so, or maybe or in late 90s, that the Gromov-Witten invariants carry the same amount for the 4-dimensional symplectic manifold. The Gromov-Witten invariants carry the same amount of information as the Seiberg-Witten invariants. There is a very specific transformation that takes one set of invariants into the other set of invariants, but the Seiberg-Witten invariants record this more efficiently. There are only finitely many which are non-zero, okay? While the Gromov-Witten invariants, sort of have infinitely many non-zero in some examples. Okay. Of course, there are also some conjecture. There are various attempts to make sense. There are some conjectural approaches to defining these numbers for Calabi-Yau threefolds in the symplectic category, but they're not. The story is not complete, and that's not what I want to discuss today. So what I want to mention is that this integrality part of this Gromov-Witten conjecture, the way I stated it here, was proved earlier in joint work with Tom Parker, perhaps maybe like 5 years ago or so, and I've talked about this extensively. Many of you have heard me talk about it. But the finiteness part, which is the part I would like to emphasize more today, was proved recently, just this beginning of this year, in joint work with Aleksander Doan and Thomas Walpuski. And I should also mention that there are related conjectures of the same sort for other types of Gromov-Witten invariants of threefolds. For example, for real Gromov-Witten invariants, in other words, counting holomorphic curves or invariant under an evolution, under anti-symplectic involution or a complex conjugation. And this is a joint work in progress with Penka Georgieva. And I think she gave a talk, I know for sure she gave a talk because I was there. She gave a talk earlier this year about part of that project in this seminar. There are many parts involved in proving this, but she gave a talk. On one part of that project, and there are other conjectures, for example, for open Gromov-Witten invariants and so on. Any questions about this conjecture or anything else?
So these
Go
numbers,
yes.
NAG, they
Yes.
have their definition is kind of gauge theoretic, similar to Seiberg-Witten, or
so they are unfortunately not. So not for the purpose of our work. So there is again, Doan and Walpuski have a conjectural. There are supposed to be some sort of generalized Seiberg-Witten invariants, and we are supposed to look at. conjecturally, we would count solutions to this generalized Witten invariance in 6 dimensions, and then we would have something similar to Taub's theorem. But again, those invariants are not yet well defined. Not known. Not completely. Their definition it's not yet fully completed. And also the relation, between the Gromov-Witten invariants and those. There are some calculations in some simple cases where there are some evidence that may work, but it's unclear that this would work in general. So yes, so for the purpose of this talk, these numbers are just obtained by making this if you want strange change of variables.
I see. Thank you.
Sure. Other questions? And in fact, as I was saying, it looks if you look at if you think about this transformation or this conjecture, it looks like perhaps these numbers would count embedded curves, okay? Embedded J-holomorphic curves in a Calabi-Yau threefold. And it's not exactly the case, but it's fairly close to it. So what we're able to prove, it's actually a structure theorem, and that's if you want the main focus of the talk. That for any symplectic Calabi-Yau threefold, there are these other invariants which we call elementary invariants, okay? And another specific transformation, okay, that transforms the Gromov-Witten invariants into this other invariants called EAG, okay? And so that after you do this transformation, these new invariants satisfy both integrality and finiteness properties. So they are the very same properties. They encode the same amount of information as Gromov-Witten invariants, but in a more efficient manner. They are integers and they're finitely many non-zero in each homology class. And the transformation is different. Okay, so it's a different transformation that transforms the Gromov-Witten invariants into this elementary invariant. Okay. And here is a transformation. The transformation looks very similar as before. You take the generating function of Gromov-Witten invariants, and it's a sum of these numbers times some other basis of power series. But the interpretation for this generating function G sub G, it's not before it was some sum of 1 over k sine of k p over 2 to some power. The interpretation of this is actually that it's the contribution of multiple covers of what we called elementary genus G curve. Okay? And not only that, this actually can be specifically calculated. In fact, can be constructed, this local model, this elementary genus G curve and its local model can be constructed using work by Jun-Ho Lee. And its contribution, the contribution of its multiple covers to the Gromov-Witten invariants can be calculated using work of Brian and Parhare-Pandey. And you get the formula that kind of looks like that. I kind of wrote it in small, in lighter print simply because it may look a bit scary. But again, it's some specific formula. It's the sum over all degrees, the sum over all partitions, the sum over all boxes in the Young diagram of the partition, and then something, this is the hook length of a box in the Young, so in the Young diagram. So it's some combinatorial. It's a very specific combinatorial quantity. It's not important, it's a specific formula. It's not important for the purpose of this talk. And maybe the other thing I should mention is that though it doesn't look anything like it, for genus 0, this is the same as the function before. So let me just say it this way. If you let the G to be 0, this elementary invariance EAG equal to NA, well, in genus 0. Okay? But in higher genus, they start being different. Okay, so they're not equal. However, what you can prove from this structure theorem, you can take this generating function, this function over here, apply to it the Kopakuma-Waffa transform, and actually you get out of it integers which satisfy. So I wrote it down. If you take the GV transform of this function, you get coefficients which satisfy both integrality and finiteness properties. And so in particular, you get that if you define the BPS states as the result of the transformation of the very specific transformation that takes Gromov-Witten invariants into this other BPS states, then these BPS states are just a linear combination with integer coefficients of these elementary invariants. Okay, so again, these guys encode sort of a more fundamental or a more they encode the same information as Gromov-Witten invariants, but in a much more efficient manner. And it actually turns out as a consequence of our right. So it's a count, as I said. Well, let me just stop here. I'll say it in the next slide. So there are these other invariants, right, that carry the same information as the Gromov-Witten invariant, and then the Gromov-Witten invariants are just you count these curves, these elementary curves, and then you have the contribution of their multiple covers, as we were hoping before. Any questions? So it looks like, so the next question I wanted to ask, can we count simple maps or simple curves, right?
Sorry, Eleny.
Yes, go ahead. Yes.
So in the end, when you conclude the Gromov-Witten conjecture, you conclude it for all symplectic manifolds?
For all symplectic okay. So we concluded for all 3-dimensional, 6-dimensional symplectic manifolds.
Okay, that's what I meant. I mean, yes.
To be honest, yes. But here that actually, so it's a slightly different formulation for those which, there is a separate formulation for what's called Calabi-Yau classes, for which the first term class is 0, and then for the classes for whatever positive Fano classes for which C1 is positive. And that's actually easier for C1 positive. So that's why I'm ignoring it, and I'm just doing it for Calabi-Yau threefolds. But yes, it's true. It's so both finiteness and integrality is true for any symplectic. As stated here with this very specific formula, it's true for any symplectic Calabi-Yau threefold.
Okay, but there's a semi-positive version.
Yes, there's a semi-positive version here, which I'm not stating. Yes. Thanks. So it's true. So it's in fact true for all symplectic, but 6-dimensional. They have to be 6-dimensional. Somehow, if it's not 6-dimensional, well, I can say then the genus appears in the dimension formula, so the techniques break down. I mean, they could be 4-dimensional or 2-dimensional, right? But more than 6 somehow, anyway. Sort of things could go bad.
Great, thank you.
Sure. Other questions?
Yeah, I had one question just asking about the consequences of finiteness for the original GW invariants. Does that imply that for G sufficiently large, everything's a multiple cover or something like this, or?
Okay, so you mean, okay, so what, okay, so maybe I'll say what we actually are able to prove, or what we can prove, but what it implies that it doesn't imply that the Gromov-Witten invariant vanish, but it implies that this elementary invariant vanish for large G. And in fact, right, so that's a very good question. In fact, sort of combining with the work on sort of superrigidity, one can also conclude that for generic J, for generic J, if you look in a fixed homology class, there are only, there is an upper, so right, you cannot have curves, right, so there is a maximum genus of curves in that homology class for a generic J.
Thanks.
But this will follow from the compact, this will follow from the results I want to discuss later. But yes, so in particular, the genus cannot go to infinity in a fixed homology class. For embedded curves, and for generic J. If the J is not generic, or if the curves are not embedded, then it could go to infinity. Okay. Other questions? All right. So the first sort of question is, could we count? How can we count simple maps, or if you prefer curves? Let's think of. There were various perspectives, but can we count them? And the first result, which is standard, is that again, we're in a Calabi-Yau threefold. For generic J, for generic parameter J, all the simple means not multiple covered, all the simple J holomorphic maps are embeddings with disjoint images. So if you look at the picture in X, you see all these embedded curves, whatever the images, you see them, they're all embedded, disjoint from each other. Okay. And in fact, something more is true. If you look at the space of such simple J holomorphic maps for a fixed J, it's a 0-dimensional manifold. Okay. So in particular, it's discrete. It has a discrete topology, and in particular, it's countable. Okay. These are, it's separable, so it's countable. Okay. But so you would think that, okay, maybe we can count. The problem is it's not, at least a priori, it may not be compact. And a priori, you could have a sequence of simple J holomorphic maps, which would accumulate to a multiple cover. So I try to draw a picture here. I drew only one element in the sequence, but this is kind of a curve that kind of looks like maybe like it's, okay, as I make them come closer and closer, maybe I have a sequence of curves that accumulate as a threefold cover of this simple curve. Okay, so a priori, at least, just from this result, a priori that may happen. Okay? However, that's not the case. So Wendell also fairly recently proved that that's not the case. That what's known, for generic J, all the embedded J-holomorphic curves are in fact what's called super rigid. I didn't define here what it means super rigid, but it just means that if you look at their multiple covers, they are isolated to first order. So in other words, you cannot push multiple covers off the curve to first order. And in particular, what this means, if you look at the space of multiple covers of one of the such curves, that's both an open and closed subset of the moduli space. Okay? And so in particular, it has a well-defined contribution. And not only that, but this contribution is given by the Euler class of the obstruction bundle. The obstruction bundle is the co-kernel. Okay, so there is sort of all these curves are super rigid. So in fact, this doesn't happen. Okay. And so as I was saying, the curves are super rigid, and in particular, their multiple covers have a well-defined contribution. And so in principle, we could count embedded curves. Okay. However, if we just count them as such with sign, they won't have any automorphism because they are embedded. We won't get an invariant, and the contribution will also not be invariant. The contribution is the Euler class of this obstruction bundle, but as you vary the J in a one-parameter family, the number of embedded curves may change, just like it was happening in Taub's case. And also the contribution could change in a one-parameter family. Okay, and so the question is, what really happens in a one-parameter path? For generic J, yes, they're super rigid and they have a well-defined contribution. But what happens in a generic path? The complete behavior is not known yet. However, again, very recently, and there was another talk in the seminar earlier this year by and Swaminathan. Where so they did a special case, but a very important case of bifurcation of multiple covers. They showed that in a generic path, again, under some assumptions, in a generic path, you could see like embedded curves, and then suddenly you could see a multiple cover of this embedded curve pop out and become embedded, right? So sort of you could see in a generic path, you could see this movie going backwards, right? So you've got the curve moving around, and then suddenly this three-fold cover, perhaps, or whatever they did, a two-fold cover, the two-fold cover pops out. I mean, not pops out and becomes an embedded curve. Okay, and in particular, the number of curves changes, the embedded curves changes, and so does their contribution. And they actually have a specific formula how the contribution changes in the case that I consider. Okay? But the complete behavior, sort of the complete bifurcation analysis is not done yet, and so what else can you do, right? So in particular, I mean, in principle, yes, one should be able to count embedded curves with weights. Okay, so we shouldn't be counting them. We shouldn't just sum them up, but we should count them with weights, so that when in a one-parameter family, what happens is the number of curve changes, but also the weights change, and so altogether you get an invariant. That's the idea. And in fact, as a consequence of our result, if you combine the structure theorem I was mentioning earlier with Wendel's super rigidity result, you can see that for generic J, I mean, the proof of it, not the statement, but the proof of it, you can see that for generic J, there is a well-defined count. This elementary invariant I was mentioning, this is nothing but a count of embedded curves, really, with weights, a weighted embedded count of embedded curves, and the weights are sort of the weights. I mean, we just know the weights they're integers, and they're finitely many, non-zero in each degree, but we don't know what the weights are. I mean, we can't tell you what the weights are. It's an existence proof. It's not a calculation. Any questions about this? So in principle, you can count them, and you can count them with weights, but I mean, well, okay, you can count them with weights, but if you just try by hand to count them with weights, the complete behavior is not known, so you don't know this. So how were we able to prove the structure result that I was mentioning earlier? And that's the question here. So it turns out that to get the structural result I was mentioning earlier, you actually don't need to know that generically the curves are super rigid. Okay? And you actually don't. I mean, you still need to understand what happens in a one-parameter family in a path, but you only need to understand what happens in the path. The bifurcations, not for multiple covers, just for simple curves, just in their own degree. Okay, that's all you need to know. Okay, and that was sort of the approach that we took in an earlier work with John Parker. With Tom Parker. Sorry. You can bypass all these super rigidity questions and bifurcations of multiple covers. you can completely bypass that and work with what we call clusters of curves. So even if you have a sequence of curves like I drew here, converge, well, I drew one of them, but imagine them converging, a movie where they converge to a threefold cover of this curve. If you look in the space of solutions, you see one point. Let me draw it right. This is our limit. This is our curve C in the limit, and then you see the sequence of curves, right, converging to it. Okay. But remember, for generic parameter, we have countably many such curves, right? They may accumulate, but they're countably many. And so, in particular, we can find what clusters of curves are just basically balls in Hausdorff distance, so that there is no curve exactly at distance epsilon. And if there is no J-holomorphic curves exactly at distance epsilon, that means it intersects the space of solutions in an open and closed set. And in particular, so that's our clusters of curves. What's a cluster of curves is just we have a ball, we have the center curve, and then it's a huge mass inside, which we can't see, but it has a well-defined contribution to the Gromov-Witten invariance, and that's all we care about. And there is a mass outside, which we can't see, but whatever, it has a well-defined contribution to Gromov-Witten invariance. And so we were able to split the Gromov-Witten invariance as a sum of these local contributions in a neighborhood of, into these clusters of curves in a neighborhood of an embedded curve, and then prove, do some wall crossing formulas for that, and prove. Prove just integrality. Okay, and if you think about it, the picture I drew here is not a picture in the space of maps, because it doesn't converge to C in the space of maps. It converges to a multiple cover of C in the space of maps. What we really looked at these curves, we really looked at them as subsets, if you want. Okay, subsets of X. Okay, and we were only able to prove integrality because we were using Gromov compactness at some point, and Gromov compactness requires an a priori genus bound, and so we couldn't show that these things. I mean, as the genus was going to infinity, we had absolutely no control, so we couldn't prove any kind of vanishing result as the genus was going to infinity. Okay? But in this recent joint work with Doan and Walpuski, we are using some results from geometric analysis, geometric measure theory. And some earlier result actually due to Doan and Walpuski, and upgrade the perspective. We're not going to look at them as subsets, but we're going to look at them as, if you want, subsets with multiplicity, or images of holomorphic curves with multiplicities, or if you want, as currents. Okay, delta functions supported sort of on this sets, just like Taubes did. Okay, in his approach proving Symplectic equals to Gromov. Okay. So let me talk. So if you want, I now finished all the introductory or motivational part of the talk. Let me now say a few more words about the pseudo-holomorphic cycles and the notion of geometric convergence. Okay, so we're not going to look at maps modulary parameterization with Gromov convergence, but a more convenient way for our purpose to look at these curves is to look at let's follow Taubes and think of a J-holomorphic curve as the image of let's say a simple J-holomorphic map. Okay, so I have I have the picture before, but I have the image of a J-holomorphic map, and the image could be singular, but it's simple. Okay, so it's sort of not multiple cover, right? So it's kind of there is a factorization theorem that says every J-holomorphic curve can be decomposed as a composition. If the domain is connected and smooth, it can be decomposed as a simple one composed with a branch cover. Okay. All right, so that's what a J-holomorphic curve is. And so, but I want to think of it as a current. Oh, and my picture disappeared. I should have drawn the picture later. But here is its image. Right, so this is X, and here is the image. I really want to think of it as a subset of X, if you want, or the image of a J-holomorphic map. So I can consider the current, right? I can look at the delta function. Think of it as a delta function supported on C. Okay. So the current, it just takes a compactly supported two form, and you integrate it. You pull it back by the map and integrate it along the domain. Right? So that's the current. And as a current, then it has a mass, or if you want, the area of the image. The mass is the same as the area of the image, and is the same actually as the energy of the map. and it's topological. It's just the same as omega evaluated on the homology class of this. Okay, so as a current, right? It's like a delta function supported C, and it has this mass which is topological, omega evaluated on C, on the homology class of C. Okay, and the support is of course C. Okay? Any questions? So that's how I want to think of the image, right? This image as a subset, but really as a current. It has this mass and has support, of course. And so now I can take formal linear combinations of these with integer coefficients, again, for positive integer coefficients following taus. Okay? And so we'll call these guys J-holomorphic cycles, right? So they look like that, right? Images of J-holomorphic curves, and we've got a bunch of multiplicities. Each component has some multiplicity, positive but integer. Okay? If you want, think of multiple cover, right? Sort of the degree of the multiple cover, if these were multiple covers. And so we'll call C of X the space of such pseudo-holomorphic cycles with the natural topology, which is geometric convergence topology. Okay, so it's not Gromov convergence topology, but it's what's called geometric convergence topology. Let me define you. I didn't define you Gromov topology, but it may be more familiar to more people. What is the geometric convergence topology? Again, this notion is due to taus. A sequence of J-holomorphic cycles geometrically converge if their supports converge in Hausdorff distance. So their supports are compact subsets, and if their supports converge in Hausdorff distance, right, that's one of the conditions. And then the pairings have to just weakly converge. Okay? That's the notion of geometric convergence. And it makes this into a topological space. Any questions about this? All right. So then, of course, we have a collapsing map that goes, remember, this is the moduli space of stable maps up to reparametrizations, or pseudo-holomorphic maps up to reparametrization. And these are just cycles, right? J-holomorphic cycles, pseudo-holomorphic cycles. So there's images with multiplicities, right? And so we have, oops, sorry, oops, I apologize. We have such a collapsing map that takes a stable map, right? Here's a picture of a map it has a bunch of components, maybe a nodal domain, and it just takes it to its image, but with multiplicities, right? So if, for example, on this component sigma 1, this is whatever 3 to 1 cover, then you remember this multiplicity, right? This M1 would be 3. Okay? And so it takes a stable map to its image, but with multiplicities, okay? And it's continuous. Okay, it's very easy to see that if it converges in Gromov topology, it also converges geometrically. And notice that with this, because we're keeping track of these multiplicities, this collapsing map preserves the homology class, but it completely loses the genus. Okay, which could be bad or good. You can't, if you just look at this, you got a bunch of curves with multiplicities, you can't read off the genus from just this information. Okay, you can read off the genus from here, from the domain, but in this picture, the genus is lost. And that could be bad, but it actually could be good in our case, because we actually don't we don't have, we want to allow the genus to go to infinity. So it's actually an advantage, not a disadvantage in our case. Okay? And I drew here an example. This is really a collapsing map. It takes all the degree M covers to just one point, okay, regardless what their genus. So there are many degree K M covers, and this collapsing map takes all of them to just one point, which is the cycle M times C. Okay, so it collapses a lot of information, and it remembers just the important. Well, okay, it still remembers some of the important information. Okay. Questions? All right, so what are the properties? Okay, so the important properties that make this finiteness result work is that we have to replace Gromov compactness for maps, which requires an a priori genus bound, not just an energy bound, right? For example, a fixed homology class, you also have to fix the genus or have an upper bound for the genus, a priori upper bound for the genus. Instead of that, we use recent geometric analysis results for currents. Okay, or if you want J-holomorphic cycles. Okay, so we're going to look at these things as J-holomorphic cycles or as currents, not as maps, mod reparametrization. Okay, and so the first result, and this is an earlier result due to Doan and Walpuski a few years back, is that this parallels Gromov compactness. It says this map. Well, projection, right? If you go from the space of J-holomorphic cycles, you project onto the parameter space, and then you look at the mass. This map is proper. Let me just, translate this. I mean, maybe this is a quick way to say it. What this really means is that if you look at J-holomorphic cycles, and you fix the homology class, then that space is compact. Okay. Because if you fix the homology class, then the mass is fixed. Remember, the mass was omega on the homology class. Okay. So if you fix the mass, I mean, if you fix the homology class, then you fix the mass, and if you fix the J, right? So if you look at J homomorphic cycle, that space is compact. It's just like Gromov compactness, except that it doesn't require a priori genus bound. Okay. It requires just if you want an energy. The mass was the same as the energy of the map. The mass of the image was the same as the energy of the map. Okay, but without the genus bound. Okay, and maybe I should say, so the way they proved it, so it's an earlier result. The way they proved this result is they combine a sort of a classical compactness result for currents, but then in the limit you get some current with a regularity result. Right, so there is this sequence of papers by the Lelis, Spadaro, and Spalaor. Sorry, I wrote it kind of small font. Maybe I can zoom so you can see it. But they prove a regularity result, okay, for what's called semi-calibrated current. So let me just say it, right? So if J is compatible with omega, then we know that holomorphic curves are actually minimal surfaces. So in particular, they are what are called calibrated things. There is a notion of calibration. And if it's only tamed, then it's in fact semi-calibrated. And so there are these results, more general results, geometric measure theory or geometric analysis result, regularity result for semi-calibrated currents. So combining sort of this, compactness result and the regularity result, one gets this specific result for J holomorphic cycles. Okay? That it's if you fix the homology class, for example, then and the parameter J, then you get a compact set. Okay? And I should also say that earlier on, of course, this result was proved by Taubes in the process of proving Symplectic equals to Gromov. But it was not clear at that particular point how that result would extend, and it took sort of this work, this regularity result, this more general regularity result in geometric measure theory to combine and get it in higher dimensions. And by the way, these results are true in any dimensions. Okay, so they don't use Calabi-Yau or 6 dimensions. Okay, so that's one result, and there is another important regularity result, if you want. That again, it's as a parallel. So this is parallel to Gromov compactness for maps. There is a sort of, if you look at the space of maps, the fact that the map is simple, or the fact that the image is an embedding, or the map is an embedding. These are open conditions on maps, and they're quite obvious. They're open conditions on maps. There is a parallel result that says if you look at a J holomorphic cycle, if you look at simple ones just means they have multiplicity 1, right? So all the multiplicities are equal to 1 on each of the components. Okay. If you look at the subset of simple ones, or if you look at the ones with subset of embedded ones, it means their support is also embedded, right? So it's an embedding, it's smooth. These are open subsets. Okay. So this is not, I mean, this is a bit harder to prove this is not as obvious for J holomorphic cycle as it is for maps, but it follows from, again, from some geometric measure theory, from geometric analysis results. So follows from monotonicity result combined with what's called Allard regularity theorem, regularity result. Okay. So we have, instead of using Gromov compactness, sort of the standard result for maps, we're going to use sort of this result for cycles, these two results for cycle, this compactness, and if you want, this open conditions, that being embedded or being simple, it's an open condition. Okay, and let me sort of translate that in a more digestible manner. So remember that we have a bunch of maps. If you want to look at curves. Okay, we can look at curves as maps mod reparametrization. So we get this moduli space of stable maps. We have a collapsing map that takes them to cycles. So these are images of such maps, but with multiplicities. And then we can forget the multiplicity, just look at the support and get into subsets. Okay, and all these spaces have topologies, right? This one has Gromov topology. This one has the geometric convergence topology. The subsets also have a natural topology, that convergence in Hausdorff distance. Okay. And this is a continuous, right? These are continuous maps. Okay. And a useful proposition, I mean, it combines some of the results I mentioned earlier together with a few other results, is the following, that if you fix the homology class, so we're going to fix the homology class, and consider the restriction of this collapsing map that goes from stable maps with Gromov topology, but embedded ones, right? So we're going to look at that. We're going to look at maps representing a fixed homology class and embedding, right? Embeddings, which are embeddings, and we're going to map them into cycles, right? So you know, anyway, this is a homeomorphism, okay? I mean, it's obviously a bijection, I think, but the result is that actually it's a homeomorph, and it's also continuous. The important part is that inverse is also continuous, okay? So it's a homeomorphism, and moreover, the image, it's an open subset of this cycle space. And let me sort of state one more thing, and then I'll stop. In fact, right, so if you restrict yourself to a fixed homology class in embedded things, right, then these things, right, these maps are all injections, okay? And the Gromov topology is the same as the geometric topology, and it's actually the same as the Hausdorff distance topology. That's sort of a consequence of the results I stated earlier. So basically, if you only care about embedded things and you fix the homology class, okay, then it doesn't really matter, right? It doesn't really matter if you put on them the Gromov topology or the geometric convergence topology, or even if you think of them as subsets with Hausdorff distance topology. Those are all the same. Okay. Any questions? So maybe any questions about this? So this may look sort of trivial, but let me give you a simple consequence. So one of the things that this implies is that if you have a sequence of embedded curves converging to an embedded curve, so if the limit is embedded, then for large genus, all the curves have to have the same genus. Right? That's what because that's the property that is the property of the Gromov topology. The fact that the geometric convergence or Hausdorff distance convergence, right? The fact that this thing, the fact, right? So let me say it this way. So this is I mean, this looks kind of trivial, but it's actually not. Right? The fact that if you have a sequence of curves Cn converging to a limit C, and they're all embedded, right? And they converge maybe in Hausdorff distance topology if they converge in Hausdorff distance, okay? And this is embedded. Actually, it's exactly something stronger, right? If the limit is embedded, the curves have to be embedded before as well. Okay. If the curve is embedded, if the limit, if the limit is embedded with multiplicity 1, then the curves before have to be embedded. Okay. And moreover, if the curves before are embedded and they converge, they have to have the same genus for large n. So you can't have genus go to infinity, for example. Okay. All right. And the other thing I should mention, these are sort of tricky, I mean, sort of fairly delicate results. This is, oh, sorry, this is not true, right? So this statement, the statements I made here, these statements are not true if we replace embedded by just simple. Okay, so if you replace here embedded by simple, this is actually no longer a homeomorphism. Okay, it's still open, but it's no longer a homeomorphism. In other words, the notion of Gromov convergence is different than geometric convergence, okay? And there are counterexamples. And it's also not true if you keep the embedded but you don't fix the homology class. If you keep the embedding and you don't fix the homology class, this part, let's see which one fails if you don't fix the homology class. Hold on just a second. Right, so the geometric topology is different than the Hausdorff topology. Right, so there are examples where it geometrically converges to a multiple cover, but in Hausdorff distance, right? So it converges in Hausdorff distance, but not geometrically, because it would converge geometrically to a multiple cover, not by subsets. Okay, so
is it because mass is not fixed?
Excuse me?
Is it because mass is not fixed?
Yes, if you want.
All right. Okay. So if I have, say, a bunch
but you see, there is no notion of mass here, right? So a subset, you don't see the mass, but you see the mass here and here. Yes, go ahead.
But if you have, say, bounded masses, then can you still have a similar result? Like you
so again, it's compact, right?
If
you bound the mass, you got the compact set.
Yeah.
But the question is, do you really have the same topology, right?
Okay.
In other words, is the notion, I mean, so right, what question are we asking? Are we asking the question whether converging as maps in Gromov topology is the same as converging in geometric topology, or are we asking the question whether it's compact?
Okay, sure. And that may break down if you have more than one homology.
Right, right.
Okay, okay. Thanks.
Okay, so there is actually a difference. Convergence as maps versus converging as you know, sort of as cycles with multiplicity. Okay. Other questions? Sorry, there is no difference. Sorry, there is no difference. So, okay, sorry. This continues, I mean, I actually don't need to fix the A, okay? You know, in order to get this a homeomorphism, I don't need to fix the A. Okay? But I do need to fix the A in order to get this equality between the geometric topology and the Hausdorff topology. Does that help?
Yeah, thank you.
Okay, sure. Other question? I mean, I try to state one result in the form that we're using it, but right. So anyway, so what, you know, just very briefly, you know, what's the proof then of the Gopak-Mavafa finiteness conjecture? So as I said, you know, we had an earlier argument with Tom Parker that only allowed us to prove integrality, but we couldn't prove finiteness because we were using Gromov compactness and we couldn't control the genus. So, you know, basically the proof, you know, once you have this geometric analysis results, sort of these results about currents coming from geometric analysis, you just use these to upgrade. So we had this, what we call the cluster formalism, you know, this cluster, you know, decomposing the moduli space into clusters of curves and then seeing what happens to the clusters of curves as you deform things. You just upgrade that argument to basically, you know, that argument proved integrality, but, you know, using this new compactness result, you just upgrade this argument to simultaneously prove both integrality and finiteness. Okay, and so in particular, I mean, what we actually prove is the structure theorem I stated earlier, which is all we needed, and then from it, just from combinatorics, it follows the Gopak-Mavafa conjecture. Okay. I think, let's see, let me just ask. So is the talk, I think the talk is what? Am I done? Am I over time, or do I have?
You're not over time. You have basically another, you know, 5 to 10 minutes.
5 to minutes.
If you want it.
Well, I don't know if I
just
want it. I can just put one slide. So, you know, I only focused. So as I said, because many of you have heard me talk about this before, in front of this joint work with Tom Parker, earlier joint work with Tom Parker, I tried to focus today more on the new ingredients involved in the proof of finiteness. Of course, there is some overlap because, as I said, the proof really is just an upgrade of that argument. Maybe just I'll finish by giving you sort of the same slide. You know, just the outline, how you prove it. I mean, this is the same proof as integrality, but now it also follows. It also proves finiteness. So they're really improving the structure theorem, and with it, this Gopak-Mavafa conjecture. They are really, if you want, 3 main steps, or 4. I listed 4 main steps, but really the three are the crucial ones. So the first step is this cluster decomposition, where I was saying we use the fact that we have countably many curves and sort of this balls in Hausdorff distance to decompose the moduli spaces as disjoint union of open and closed subsets. These balls around embedded curves in Hausdorff distance. And so reduce proving the Gopak-Mavafa conjecture or the structure theorem to just a local statement, just in a neighborhood, an epsilon neighborhood of an embedded curve. Okay, so we've got sort of for one of these clusters of curve, right? So this cluster of the curve is just one embedded curve, you know, and there is a ball in Hausdorff distance epsilon around it. Well, maybe I should have used a different color for this ball. And oops, sorry. I apologize. No. So these are clusters of curves. So just proving it for one side, proving it for every single cluster of curves. Okay? Another important piece of the argument is actually this elementary contribution. We have to be able to construct by hand a local model, a very specific local model. So if you give me a genus G curve, I have to construct a particular local model so that I can calculate. So, I can understand what happens in a tubular neighborhood, and I can calculate the contribution of it to the Gromov-Witten invariance. And not only that, but when I say by calculate, I have to explicitly calculate, so I can verify that if I make that crazy change of variables, it satisfies this Kopakuma-Buffer conjecture. I get integers and finitely many. And that construction I mentioned earlier, this used the work of Junho Lee and Brian Panharipande. And then the last piece of the argument is to isotope. So deform, cluster isotopy, deform the J we started with to this elementary one where we can calculate everything and see what happens to the contribution. So you have to prove some word crossing formulas. But these are sort of simple word crossing formulas. You just need to understand what happens. Basically, you just need the Kuranishi local model for the moduli space of stable maps. Excuse me. In simple stable maps, right? So you just need to work with simple maps in their homology class, in their genus. If you know that, what happens to them, that's all you need to know. Sorry, and the rest is just an induction argument. Once you have this, you can conclude by induction that the local contribution is a finite linear combination of this elementary contribution with integer coefficients, and it's finite, right? Finitely many non-zero in each homology class. And I think I mentioned this earlier, so I shouldn't. Right, there is this joint work with Penka Georgieva in progress for this real Gromov-Witten invariance, and she was talking about she was talking about part of it. Again, constructing this local model and calculating contribution, it's highly non-trivial, and so we had to redo these calculations. They weren't available. we had to do something and had to do the calculation for this real Gromov-Witten invariance. But the finiteness should hold. Again, the rest of the argument should carry through in that setting. And we kind of expect a more general structure theorem, but exactly how it looks like, it's unclear. So let me stop here. I guess.
Thank you. Let's thank Eleny. And then, are there any questions?
Could I ask maybe about an application?
Sure.
There's always the question of the convergence of the Gromov-Witten.
Oh yes. So what this implies is that there are analytic functions
for the semi-positive.
For Calabi-Yau, for symplectic threefolds. For symplectic threefolds, this means they're analytic in the genus. So they're converging series, right? They're actually rational functions.
Okay.
Sorry, they become rational. So I had this sign. Normally one makes the change of variable e to the t, which is very unnatural, but whatever. One denotes e to the t by something else, u, and then they become rational functions in u, in this u variable.
Is that expected to hold for higher dimension as well, or it's just not known?
In higher dimensional symplectic manifolds.
Yeah.
I don't know. Again, see, once you move in higher dimensions, maybe it automatically holds, because in the dimension formula, I think you cannot write as the genus increases, the dimension goes down, right? So it's really only for Calabi-Yau threefolds that there may be a matter of convergence, right? So if you look at the dimension formula, it's the dimension of x minus 6 times 1 minus genus, right? So if you are doing dimension of x bigger than 6, then there is a, if the genus is very large, then the dimension will be, if you fix the homology class, right? And the genus is very large, then you get negative dimension. So so it's really only only threefolds. And that's a matter. So yes, that's one of the consequences that you get. Whatever the physicists were saying, that these are converging power series, right? They're analytic functions. That in fact they are. Gromov-Witten series are analytic. I actually never thought with the case, but anyway, it just they are. It turns out it's true.
Any other questions? I wanted to ask, when you say that there is a more general structure theorem, what does that refer to?
Well, okay, so I was again, so okay, so what I mean by that is, so it would work perhaps just for semi-positive manifolds, maybe more general than semi-positive manifolds, but certainly what you can do, you can start with a moduli space, of stable maps and map it to this cycle space, right? The moduli space of cycles. And that collapses a lot of things. And so what you expect is that actually maybe you can count cycles, right? So and then have a general, I mean, right, you get a count of such, you get an invariant, right? I mean, so certainly you can always push forward the virtual fundamental class, right? This is a question, right? So I can go a bit more technical. You can push forward the Gromov-Witten virtual fundamental class to the cycle class, but I actually expect maybe the cycle class to have their own fundamental class, perhaps, or whatever, some contribution, and the Gromov-Witten class would be these guys with multiplicities. I mean, well, okay, or maybe all a class of some bundle or something like that. So maybe a decomposition, right? Maybe a decomposition of the Gromov-Witten invariants coming from contribution from cycles and sort of some Euler class of, well, some sort of virtual Euler class of some obstruction bundle, something like that, perhaps.
Okay.
So because there are some similar conjectures, right? I mean, to some extent, that's what happened for threefolds. For generic J, these curves were super rigid, and therefore, the Gromov-Witten invariance, it's a count of sort of embedded curves, but with weights or whatever, with contribution coming from the Euler class of the normal bundle. Mm-hmm. And so you can actually count sort of embedded curves, right, separately with different weights to get a more refined invariant. And there are similar kind of conjecture, and there are some similar sort of formulas for Calabi-Yau 4 folds and maybe 5 folds, like for genus 0 or for genus 1. They're supposed to be this more elementary invariants. But perhaps, yeah.
Okay. Any other questions? Yes, Chris.
Maybe I'll also ask another question, but does this include descendant invariants?
So for Calabi-Yau 3 folds, again, all moduli spaces are 0-dimensional, so there is no room to impose any other conditions.
But I guess.
But for the other one, right? So okay. So because I'm going to the cycle space, I'm completely losing the information about the domain. Okay. And so this would only apply to what are called primary Gromov-Witten invariants, where you just cut down by imposing condition. They pass through a bunch of constraints. Maybe they are tangent to something, but well, okay, maybe tangent may also not descend, because if you reduce it, you may lose the condition that it's tangent, or unless you kind of keep track of the multiplicity. But if it passes through, it certainly behaves well under this collapsing the multiple cover. So yes, it will only be the primary Gromov-Witten invariants. Though I have to say that for Donaldson-Thomas or Panhari-Pandit-Thomas invariants, there are versions of them, for, including descendants. So, perhaps one could have an upgrade of this. I mean, perhaps if you really want counted curves with maybe bundles, with the right. I mean, if one had a correct a better geometric PDE that would count the solutions. Perhaps one could be able to maybe recover the genus or upgrade it to descendants. I don't know.
Okay, thank you. Maybe we should thank Eleny one more time.